Hey everyone. So obviously you already know I'm not feeling well today. Ugh. So I'm going to be doing the lecture over video, and we'll cover a couple things here, and then we'll switch over to the demo that you guys were going to get. All right. Okay. Let me switch this over. Okay. So unfortunately, I'm recording this a second time because I didn't have the cursor thing on. So you guys should see my cursor now, and we can actually work with that. All right. So we're going to be covering hue, temperature, value, tint, tone, shade, and intensity in this lecture. And about 90% of this lecture is just going to be hue because it's kind of the most important part of what we're talking about here. So if we jump through. Okay, so what is hue? Hue is an electromagnetic wave. Electromagnetic wave. It's a part of the magnetic wavelengths, and it's what we refer to as visible light. We detect it with our eyes because this is, and we call it the visible spectrum because it's what we can perceive. Um, we are trichromats, so we have, you've probably heard we have rods and cones in our eyes. Um, the cones are what we detect color with, rods is what we detect light with. We are trichromats, so we have three different sizes of cones. It's going to be small, medium, and large. You've probably heard that you have, red, green, and blue cones. That's not necessarily true. They actually detect, each of them detects a fairly broad range of spectrum, and then your brain decodes that. You've probably also heard of people who have color blindness, and that's usually when the signals between the medium and large cones or one of the other pairs fails. So that's where we actually get color blindness from. Um, One other thing I want to point out with that is, again, we're trichromats. Dogs, for example, are going to be di or bichromats. They only see two, or they only have two rods in their, or sorry, two cones in their eyes. And so they see a smaller range of spectrum than us. Similarly, there's a mantis shrimp. I don't know if you guys have heard of those or not, but they actually have 12 different types of cones in their eyes. And so they actually see not only finer detail in the colors that we see, but they can also see, I think it's at least into infrared, if not also ultraviolet. So what does that look like? Well, I have a TV remote right here with me, and if I press the button on this, I can't see what's going on, but if you look at it through a camera, you guys can see that light coming on. That's infrared light coming from the remote. And the camera's picking it up, and then it's translating it down into an RGB spectrum that we can see. One other thing I want to mention too is Veritasium on YouTube. There's a fantastic video that that channel has created about why, or basically, it's how rainbows work. It's really interesting. I would highly recommend you guys take a look at it. But that's all I'm going to say about that. All right, so let's jump forward here. We have two sort of types of color that we're working with. There's going to be additive color and subtractive color. Additive color is the one that you typically see with digital work. It's going to be your red, green, and blue. It's what our pixels are made out of, and it's what sort of theater lights are made out of. Again, looking forward to this lecture. I bought a whole thing of these theater gel things so that we could do a demo on it with cell phone cameras or cell phone lights. But unfortunately, that's kind of out now. But the idea with additive color is that you have white light being shown through. In the case of a monitor or cell phone, that's typically through a backlight. Your pixels on the computer monitor are going to filter out at each pixel one of those three colors at each part of the pixel. And then that reaches our eye because the pixel's so small is effectively the same thing. Again, back to pointillism and how the points create the whole. But when you have the white light shown through, filter out each of those colors. But when that gets reassembled, if you have full strength brightness of the red, green, and blue, you end up seeing white again. Subtractive color is a little bit different. What happens with subtractive color is that white light is shown on it, and then what it absorbs stays there, and what it reflects is what you see. So if we shine white light on a red piece of paper, what's happening, and you can kind of see that in this diagram right here, the the green and the blue wavelengths are being absorbed and the red is reflecting back. In the same way, if you were to shine a blue and green light, or a light that had blue and green but no red frequency in it, this would appear black because it would reflect the same way that the black would, in that it doesn't reflect anything. Oh, you guys probably can't see that because of my overlay. Shoot. But you can see this with the white here, where we see white because it's all three of those color spectrums, colors reflecting off. Now, subtractive color is typically referred to as CMYK, or cyan, magenta, yellow, and black. I always get questions, why is it K and not black? K stands for key, and it's specifically because they didn't want to put CMYB and have some people assume that the B was blue. So that always kind of comes up every once in a while. And again, it's white light reflected off the surface. So we have additive, we have subtractive. When we are painting, we're going to be working with subtractive color. When you're working digitally, you're going to be working with additive color. And that has some pretty important consequences that we'll get into in a minute here. So when you're working digitally, you're working with what's called a color gamut. Those are the colors that your computer is storing, how it's represented on the screen. So we have the CIE 1931 color space diagram right here, and right here along the edge you can see that we've got these different numbers. Those are the wavelengths, so you can see that here's 380, here's 750, and if we jump back to here, 380 is going to be here, 750 is going to be there, and you can kind of see that on this spectrum as well. Okay. So when you're working in an RGB color space, you typically, a lot of people will work with RGB 1988. That was always what was told to me when you're working on print. I think default for Photoshop is actually sRGB, but could be wrong there. But what's important to recognize is the shape of these areas, right? One thing that I'm constantly harping with my students on when they're setting up renders for print and putting together presentations is you'll have a really nice green right here. You'll have this teal color or whatever you want to call that. You go to print and it comes down to here because this is the color range that the CMYK color space can represent. That's just a limitation of using those three colors, of using cyan, magenta, and yellow. When you mix colors in here, it doesn't go like straight across. Like if you mix blue or the cyan and the yellow, it actually kind of follows around this perimeter. It doesn't go straight across here. But what ends up happening is that, again, as you kind of mix those pigments, they kind of, again, loop around the outside here. And so you don't end up with sort of kind of the bright colors that you'd like to see when you're going from digital to print. So keep that in mind. Now, how do we actually get bright colors, right? You've seen all kinds of things where you're like, oh, but that has a really bright color. How do we get that? The answer is Pantone matching. And Pantone is an industry kind of standard where they match these colors and they're consistent. A Pantone color is going to be outside of the range of this CMYK because it's not using CMYK. It's using the raw pigments, right? The main purpose of Pantone matching is so that if I'm a billion-dollar corporation and I want to make sure I have consistent branding, I say that I have W1497 or whatever is my Pantone code for the background on my shape. And then whoever's printing that goes and grabs that Pantone color. It's going to be consistent. It's going to be the same color no matter where you go. And it's going to be outside of this CMYK range. So that I can get that consistent branding and consistent colors. It's a little bit more expensive, but that's, the cost of doing business. But from that, you get 1,867 unique colors from 13 base pigments instead of the 3 pigments that you have here for CMYK. And I've got another graph next that'll show kind of what that effectively means. Some other things that you've probably heard of is Roy G. Biv, created by, I've heard at least it's created by Isaac Newton. There's a lot of controversy about it. A lot of people say he basically added indigo in. It doesn't really count, and so you've got Roy G. Biv. But what apparently I've heard some places he added the indigo because he wanted to have 7 steps so that it was more like a musical schedule, which very 1800s of him. If you've ever worked in print, you've also probably seen a couple printers that have extra things. So CMYK is your standard, and then there's CR, which is chromatic red. And what that's going to do is it's going to shift this triangle a little bit more out here. So you'll capture a little bit more of this range when you actually go to print. And then the PK is going to be your photo black, and your MK is going to be your matte black. And it's going to mix those in sort of based on how the computer and the printer are set up. So those are different settings there that you work with. So that's digital. This is going to be more in, again, subtractive color space, where you're working with the primary colors. We'll discuss color wheels a bit more, I think, on the next slide. But again, when you're working in a subtractive color space, you're going to be working with red, blue, and yellow. So those are your three primary colors. When you mix those two of those primary colors in each direction, you end up with your secondary colors, which are green, orange, and violet. Anything after that, anything kind of that gets out of that range, those are your tertiary colors. And the book said it best, it's basically all the other ones. People will define a color, but for example, if you look here, is this orange, or is this orange, or is this orange, right? So at a certain point, you get into those tertiary colors, whereas these primary and secondary colors are very narrow bands on there. And again, we'll see that on the next slide. But I did want to point out this this sort of version of this, where again, this is showing the whole visible spectrum. This is showing what you can typically generate with RGB. And then right here is the Pantone, this dashed line right here. So again, it uses 13 different pigments to create a wider range of colors than your CMYK range that's inside of this. So that's why, again, we're not going to use Pantone colors, but I want you to be aware of them. But when we're painting, for example, I had you guys get cool and warm colors. So like I've got these paint tubes right here. These might be outside of this CMYK range, and then one of them is going to be cooler, so it's going to be a little bit shifted this way. Other one's going to be warmer, it's going to be shifted this way. And we might have one color that's here in the CMYK space and another one that's out here. You might have a cool yellow that's kind of like over here, and then a warm yellow that's out here. So when you start getting into actual raw pigments, that's when you get kind of those colors that are outside of what's typically producible in print. We'll get kind of more into that in our demo, so we'll cover that then. All right, let's go on. So color wheels, there's a couple different kinds. The book has the 12-step ITIN. That's kind of the one you're most probably familiar with, which is going to be your red, yellow, and blue. Here's your primaries, your green, orange, and violet as your secondaries. That's your Roy G. Booth without the I. A lot of people will say, oh, well, these are your tertiaries, but really, again, like our book says, and like I've kind of always been taught, anything else is a tertiary. There's also this 10-step Munsell. I've never seen that one before. The 10-step Munsell, and then the Munsell color tree, which starts dealing in intensity, which we'll get to later in the lecture. There's, again, Isaac Newton's color wheel, which has 7 steps and kind of looks kind of weird. And then there's Philip Otto Runge, who created, back in the 1800s, this series of color globes, where he starts at white on one end and then pure intensity on the other. This is, I don't know what he's doing here, but he has a whole series of them. They're kind of cool to look at. But the idea of color globes is pretty interesting. But these were effectively the same idea as a color wheel. He's just mixing with the same values as this color tree here. All right. When we get into digital color wheels, there's a couple types that you'll encounter. Again, the typical is going to be RGB, but there's a couple that are not the same but similar, which are the HS and whatevers. And so HSB, the B stands for brightness, but it's typically your value. I've seen HSV as well. And so those are going to, there's HLS, L stands for lightness, HSI, intensity. It's all the same thing. It's just sort of displayed differently. So you might have a third what typically you have is this color area here, and then you'll have a slider in addition to that. So they're just different ways of working with the same thing. It's at the end of the day, what you're effectively doing is getting an RGB color code out of this anyway, and then from that you're turning it into a CMYK if you go to print. One I didn't include here is going to be hexadecimal color codes. Those use, what is it, 8. No, I didn't put it in here. Well, hex, yeah. It uses color codes 0 through, or no, 16. Yeah, 0 through 9, and then A through F. 2 pairs of those represent each color. That gives you 256 values between 0 and 255 for you to represent each color. That's typically what RGB on a computer is going to be doing. It just does it in a slightly different way. Some will use percentages, some will use decimal values if they're really fancy. But at the end of the day, you're typically just ending up with an RGB color gamut and then eventually sending it to print. All right, so there's color temperature. Excuse me. All right. And the temperature refers to the heat. This is both a physical value and a psychological value, right? This is the way the book represents it. Is these are kind of the cooler colors. These are the warmer colors. I've typically seen kind of orange as being considered the hottest and blue as being considered the coolest. And I've seen it split across this way. I've seen different ones where it's split into 3 chunks. So you have these 3, or sorry, these 4, and then these 4. But generally the idea is just that this is which colors feel more energetic. And then again, like I told you guys, I still have the paints right here. I told you guys to get a warm red and a cool red, warm blue and cool blue, etc. Which means that you can have warmth within a color. You can have specific colors that are warmer than others or cooler than others. So it's not a fixed, like blue is always going to be cool. You can have a warm blue. Orange is not always hot. You can have a cool orange. It's just relative to where it kind of is on the spectrum. Also for my interior architecture students, keep in mind that this is completely separate from the light texture that you guys will be discussing in your lighting class. Down here we have warm, neutral, cool, and cold colors. You'll use these in different spaces and for different reasons, but it's a completely different subject than what we're going to be talking about in this, okay? But I want to make sure that that's understood. All right, let me go next slide. Okay, so value, tint, tone, and shade. These are all kind of the same direction, or same thing, but kind of different directions. So it's the value is going to be the relative lightness or darkness of a color. The tint is represented by mixing the hue with white. The tone is represented by mixing the hue with gray, and then the shade is represented by mixing the hue with black. Some of these are going to be kind of similar to what we saw with the color wheels here, where you're dealing with different intensities, especially. So if we jump over to like your shade right here, hue with black, oops, that's going to be when you mix the lightness or value here. So we're dealing with the same ideas here, it's just represented in different ways. So keep these in mind though, but when you do mix white with a tint, or when you create a tint, it's going to be a different color. If we jump over to intensity, again, we were just talking about HSI, hue, saturation, intensity, and what we have here is it's just the color purity. Again, it's how much of the hue before you mix it with the white or the black or the gray. So when you're talking about intensity right here, you can see this first column right here is going to be the intense colors. It's pure intensity of the hue. The second column is a pure hue mixed with black as it goes through space. And then this one is going to be mixing complements. Complements are a whole other lecture that we're doing Wednesday. So we will discuss them at that point. Okay. So that is all for this lecture. I will jump into some of the stuff for that next. So I'll see you guys in that video.